Today, we're going to look at how we observe the sky in astronomy, including looking at types of telescopes and other equipment, how they work, and the different types of information they can give us about objects in space. Even though people hundreds or thousands of years ago may not have had modern technological equipment, humans have had a pretty good grasp of some things for a very long time. You don't need to memorize these items, but it's useful to see how much people knew so early on due to our ability to watch the patterns in the sky. Even so, we've still had a lot of misunderstandings until much more recently. One example is Aristotle, who was primarily a philosopher. He had a lot of ideas about astronomy too, some right, some wrong. Aristotle knew Earth was spherical, but also thought incorrectly that Earth didn't move. He believed that Earth could not be rotating because we don't feel like we're moving. There's no constant whoosh of wind all the time. And parallax is not observed. We'll get to parallax on the next slide, but it does exist. Humans just didn't have the technology to measure it in Aristotle's time. Now back to parallax. Look at the diagram. When Earth is in the position labeled January, someone looking toward the star labeled A would see other background stars behind it. 6 months later, when the observer was at the July position, the same star A appears to be in a different position, with different background stars behind it. Though the star hasn't actually moved, the background makes it look as if it had moved because the Earth has moved. You can do a simple activity right there in your chair to demonstrate. Hold one finger out in front of your face, about 8 inches away. Close one eye, then switch. Go from right eye to left eye and back again. Even though your finger isn't moving, it looks like it's moving. This is the idea of parallax. Aristotle could not observe parallax, so he did not believe that Earth was revolving around the sun. Nearby stars actually do exhibit parallax. They appear to shift somewhat over the 6-month time frame, but it's such a small amount Aristotle couldn't see it. The shifts are very small, only fractions of a degree, and you still need advanced equipment to detect it. We talked about retrograde motion a little in the last lecture. People have known for thousands of years that planets and stars are different, even before the invention of telescopes, because planets seem to wander through the sky. But stars do not exhibit retrograde motion. Retrograde motion is something easily observed if you watch a planet in the sky over the course of several days. We will look at how it appears observationally here. In this image, all of the black stars represent stars. The red one, though it looks like a star to the naked eye, is actually not a star but a planet. If you only rarely look at the sky, you might not know the difference. But let's look at how it moves over time. One day, this red object appears to be way off to the right side of the image, immediately to the left of an actual star. The next day, it will be in a different position. Here, it's moved to the left a little, and a little farther left, and a little more, and a little more. But watch what happens next. Here, it seems to have moved back toward the right side. And a little farther right, and a little farther right still. But next, it will begin to move back the other way. Back toward the left, and farther left, and farther left, and farther left still. So over the course of this 12-day span, we see that the planet has appeared to make this looping path across the sky. We call this retrograde motion. And again, only planets do this. Stars do not. So if you watch the sky carefully over the course of many days, you can tell whether an object is a star or a planet based on whether it exhibits this looping pattern or not. In fact, ancient people were so interested in these moving objects, the planets plus the sun and the moon, that they named the days of the week after them. Sunday, the sun's day. Monday, the moon's day. Saturday, Saturn's day, are relatively obvious in English. Some of the others make better sense in other languages. But all these objects can be seen in the sky without telescopes. But telescopes help to see in better detail. Telescopes are instruments that collect and focus light. There are different types, but most use either lenses or mirrors or both to make the image we see. Some telescopes are ground telescopes, meaning that they are here on Earth's surface. But others, like the Hubble Space Telescope pictured here on the left, are literally out in space, either orbiting the Earth or the Sun. When asked, many people say that telescopes make small things appear bigger. But that's incorrect. That's what a microscope does. The things we look at in astronomy aren't small. They're just very distant. They make far-off things appear closer by collecting more light. Though magnifying power can make the image a little bit better, it actually isn't the most important feature. The amount of light that a telescope can collect is what makes a telescope better or worse. Let's look at why that is. Think about what your eyes do when you cross from a well-lit area into a dark one or vice versa. Your pupils change diameter either to allow in more light if it's dark or to restrict light if it's very bright. Telescopes that are narrow in diameter, like your eye during the day, cannot collect as much light as a wide diameter telescope. But any telescope can collect a lot more light than just your eyes. A telescope is always described by its diameter. My big telescope is a 14-inch that's about 6 feet long. Since it's 14 inches in diameter, it's called a 14-inch scope, not a 6-foot one. I also have smaller telescopes, but they are not nearly as good if I'm trying to look at a faint object. Telescopes are often called light buckets. The more light you can collect in your bucket, the better you can see. Here is an image collected with a small diameter telescope. Look at the details. Look at the sizes and brightnesses of the objects. I'm going to show you the same area of sky next, but this time with a larger diameter scope, and I'd like you to compare the images. It's easy to see a marked increase in the brightness of the objects. You can even see objects in this image that were invisible in the first because these were so faint that the first telescope didn't even pick them up. Early reflecting telescopes only had one primary mirror. Since the only way to collect more light is to have a larger diameter mirror, large telescopes are in demand. It's very difficult to make very high quality large mirrors, so newer reflectors are often made of several smaller mirrors combined to make one larger one. Notice here that circular mirrors don't fit together particularly well, though. Some scopes, like the James Webb Space Telescope, are built with these hexagonal honeycomb-shaped mirrors. The advantage to this is you don't lose as much light in the gaps between mirrors as you would when trying to put circular mirrors next to each other. Larger mirrors also improve not only the light gathering capability, but it also makes images sharper. Look here at this blur. This is how you might see a distant object with a very small telescope. You can't even really tell what you're looking at. Now let's see how it changes as we use larger and larger telescopes. Using a slightly bigger telescope, here we see the same area of sky, and it's still mostly blurriness, but we see a little differentiation in some brighter areas. With an even bigger telescope, it's more defined still. And with a very large telescope, look how well defined the individual stars are and how crisp and clear the nebulosity is. Nebulosity is what we call this blurry, gassy stuff around the edges. Large mirrors, though, don't solve the problems of image blurriness when it comes to atmospheric disturbance. Astronomers use two terms, seeing and transparency, to describe the observing conditions with relation to the atmosphere. Turbulent air causes images to look distorted. Stars don't actually twinkle. That effect is actually just the atmosphere disturbing our view. Now compare these two images of the same area of the sky. The left image was taken from a telescope on the ground. The one on the right was taken by the Hubble in Earth's orbit. Because the Hubble orbits above the atmosphere, its images are even better than larger ground-based telescopes. Now compare these images of Jupiter. You can see that the left image is more blurred and that the colors aren't as distinct. The Hubble image is much clearer. You can see many more individual storm cells along the white stripe where the great red spot is. Note that those circular white storms are not visible in the other photo. This image is magnified even more by a telescope that orbits Jupiter. This detail could not be seen at all in a ground-based telescope. Only a space telescope could detect this variation in colors and cloud formations. Here are a couple more images of Jupiter, taken with the new James Webb Space Telescope. These images are colored differently because they're not taken with regular visible light the human eye detects, but by collecting infrared light. This telescope is essentially measuring the heat of objects. Notice you can see that Jupiter has a faint ring surrounding it. Now take a look at these images. This illustrates another advantage that the Hubble has over some telescopes. Our eyeballs can only see the part of the electromagnetic spectrum that we call visible light. It's really only a very small part of the radiation that's out there. The Hubble is able to detect not only visible light, but also the infrared rays that the James Webb collects. In the visible light image on the left, all you can see is the gas cloud of the Orion Nebula. However, with the infrared camera image on the right, the same area, we can pick up individual stars that are forming inside that cloud. Their visible light is not able to penetrate through the cloud, but the heat can. In this way, using different wavelengths of light actually allows us to gain a lot more information than what we can see with our human eyeballs. Here is one more picture comparing two images of a planetary nebula called the Cat's Eye Nebula. From the ground, we can see the dying white dwarf star in the center and the envelope of gas expelled surrounding it. With the Hubble, though, we can see a much crisper image with a lot more detail. And though ground-based telescopes are limited in what they can see, they're actually getting better. New technology allows us to cancel out some of the effects of atmospheric disturbance. This process is called adaptive optics, and it uses a laser to create an artificial star in the sky. Then, the instrument can see how the fake star is affected by atmospheric disturbance and use that information to correct the images of real stars. See how much less blurry the corrected image on the right is. Here's an example of how much more detail can be brought out in the photo of a planet when correcting for atmospheric disturbance. The first image of Neptune doesn't give us much detail, but we can see much more detail and streaky surface storms that come from massive winds that occur on Neptune. Different types of telescopes are designed for different purposes. Though the Hubble takes detailed images of very small areas of the sky, other telescopes are used for sky surveys, where they're trying to map huge portions of the sky. Here, this picture shows the entire sky. What we see is actually a bunch of tiny images stuck together. The Gaia telescope is making new and more refined maps like these. The new Vera C. Rubin telescope also combines images into a larger map. The Rubin started operation in 2025 and will image the sky continuously for the following 10 years in order to detect changes in the sky. It's expected to image 20 billion galaxies and millions of new asteroids in this time. One image covers an area of sky equal to the area of 45 full moons, so this huge camera will make revolutionary discoveries. Here's an illustration showing you all the different types of electromagnetic radiation, or all the different kinds of light. It may sound weird, but human eyes can only detect a small fraction of all the kinds of light there are. Visible light that our eyes can detect is roughly in the middle of the spectrum. Radio and infrared waves have too long of a wavelength for us to see them. Ultraviolet, X-rays, and gamma rays are too short in wavelength for us to perceive. You can see the scale below showing the relative sizes of the wavelengths. The reason why those different types of waves are important is that each different type of light can give us different information about the object we're looking at. Each one of these narrow strips is a photograph of the exact same thing, looking toward the center of the Milky Way. Look at the third one from the bottom that is labeled optical. This is visible light. There's not a lot to see there except a bunch of blackness. This is dust blocking our view of the galactic center. But if you look at the strip right above that, the near infrared, you see a giant bright spot in the middle. That is the heat coming from our galaxy's core. It's not visible in the lower image because visible light is blocked by dust, but the heat can penetrate through the dust, so we can see it at infrared wavelengths. Each strip corresponds to different wavelengths of light and gives us different information. Here is another image of the electromagnetic spectrum. This one, though, shows the types of waves in increasing order of wavelength instead of decreasing. The same kinds of light in reverse order. If you know the colors of the rainbow acronym Roy G. Biv, you see that it's in reverse order here. The first three types here, gamma rays, X-rays, and ultraviolet rays, are blocked by the ozone layer. If you had an X-ray telescope on Earth, it would be worthless. You wouldn't be able to see anything. Infrared rays are heat. Microwaves really shouldn't be listed here, as microwaves are a type of radio wave. Radio waves are the longest waves with the lowest frequency and energy. Remember, this tiny section of visible light is the only type of light that our human eyeballs are sensitive to. Though space telescopes are above the atmosphere and are generally superior to ground telescopes for that reason, there are some things you can do with ground-based telescopes to help. First, building them away from cities and high in the mountains really helps. It avoids the light pollution associated with electric lights at night and puts the observatory above the clouds and as much of the atmosphere as possible. As a result, Pensacola isn't a very good place to do astronomy because it's a city, it's often humid, which makes the atmosphere very unstable, and it's at sea level. If your telescope is collecting radio waves, you want it to be far from cell phone and TV or radio towers, so put it as far away from cities as possible. Take a look at how much light pollution affects our ability to see the sky. Just the lights from this neighborhood and one street light make it very difficult to see many stars at all on the left-hand side. Out far away from cities, many more stars and even the Milky Way itself is visible. Here's another picture of just how much light pollution can change in a relatively short period of time. In just 20 years, Tucson, Arizona went from a pretty decent place to set up a telescope to a much more inhospitable location. This shows you how much damage the atmosphere can do to an image. The first picture shows the stars, much larger and blurrier, made fuzzy by atmospheric distortion. The Hubble photo on the right, you can see the much clearer image. Here are some of the optical, visible light, and infrared ground-based observatories. These sites are all in locations that have very dry air, not humid air like it is here. And they're built on mountaintops, high above much of the atmosphere and many weather events. Here's an image showing you a photo taken of a home in infrared light. You can see just how much heat is lost by the house around the windows and doors. This is a similar infrared image, but this time taken of the constellation Orion. The picture on the left is just of the individual stars taken in visible light. But the infrared camera view on the right shows us so much more in the same area of sky. We can see huge amounts of heat radiating from the sword region of the constellation, where the Orion Nebula exists, but we also see a hugely bright area off to the left side. We don't see anything going on in that area of the other photo. That's telling us that something big is going on there, but that we can't see it in visible light. Probably it's being blocked by dust. Radio telescopes actually look a lot like satellite dishes. Sometimes they're a single really large dish, like the Arecibo telescope in Puerto Rico. Other times, they're a set of many smaller telescopes that work together, like the VLA in New Mexico. These telescopes have to have these huge dishes to catch the radio waves because of their long wavelengths. And remember, many types of light must be collected above the atmosphere. Here are images of several space telescopes. The Hubble Space Telescope is in orbit around the Earth, and it's big. It's about the size of a big yellow school bus. There are a variety of different places a telescope can be put into a stable orbit. It's important to know the exact orbits of these objects so they never collide. You don't need to memorize the names or types of these telescopes, but I want you to see just how much variety there is. The Chandra X-ray telescope uses a set of mirrors to deflect the X-rays into the detector. X-rays are blocked by the Earth's atmosphere, so X-ray telescopes must be launched into space. Chandra orbits the Earth in an elliptical path that brings it much closer to the Earth at perigee than at apogee. That means it travels very rapidly for a short period of time as it passes Earth, then travels much more slowly for a long time, approaching and passing apogee. These are two images taken of the Sun. The photo on the right is of the sun in visible light. Notice that it's pretty boring. Not a lot going on, just a few small sunspots. On the left, though, you see a sun that's very active in the X-ray portion of the spectrum. This shows you the location of active storm regions on the surface. This is an image taken in gamma rays. Notice that although it goes from generally more active to less active as you move out from the center, there are a few pockets of intense activity elsewhere. These indicate powerful events that can affect wide regions of space. The Spitzer Space Telescope observed in infrared light. Though the Spitzer telescope is dead and is no longer active, it was collecting heat, and it could image objects with relatively low temperatures. Though stars themselves are very hot, gas clouds can be extremely cold. Look at all the dust that's visible between the arms of this galaxy. The Spitzer telescope orbited the sun, trailing the Earth in Earth's orbit, moving slowly away from the Earth. Hubble, by contrast, orbits the Earth at about 350 miles of altitude. Here is a model of the new James Webb Space Telescope. It replaces the Hubble as NASA's main space telescope. It's named after a former head of NASA. This model of the Webb shows its honeycomb-shaped mirrors over a huge sunshade. Notice just how big this telescope is compared to the people standing around it. It's a lot bigger than school bus-sized Hubble. Webb's mirror is quite large, even compared to Spitzer and the Hubble. It's actually so big that it had to be folded up to fit in the rocket that launched it. It launched in December of 2021, and luckily it all unfolded properly when it got to its destination. The Webb sits in one of Earth's Lagrange points. You don't need to memorize the Lagrange points, but there are 5 such stable points where an object can be placed and remain in place due to the gravitational forces between the Earth and the Sun. The Webb is at L2. Here you see the Webb at L2, much farther out from the Moon, following along with Earth's orbit, always staying out of the Sun's view. Luckily, everything worked as planned with the Webb. It is so far away, much farther than the Moon, that we could not send out astronauts to fix it if something had gone wrong. Here are a few of the first images that Webb took. These gas clouds and galaxies show much more detail than other telescopes can. A couple of other important telescopes are Kepler and TESS. Kepler died at the end of 2018, and TESS launched in the same year. These scopes hunt for exoplanets, which are planets that orbit stars other than the Sun. Kepler found thousands of planets outside our own solar system, and TESS will find many more over its lifetime. Spectroscopy is an important part of astronomy, and we will talk more extensively about this in Unit 3. Spectroscopy involves taking light from a star, separating it by wavelength, and analyzing each bit separately. In this image, you can see the spectrum of hydrogen and the spectrum of helium. Each element has a unique pattern of lines. If you were to look at the sun through a spectroscope, you'd see that it's a combination of both hydrogen and helium lines. This is how we know what the sun is made of, even though we can't actually go there. When you pass white light through a prism, you get a rainbow. Using a filter, you can separate out different colors of light based on their wavelength. Blue light has a short wavelength, around 4,600 angstroms. An angstrom is 1/10 billionth of a meter. Using a different color filter, you can filter and detect a different type of light. Green light has a longer wavelength than blue. Yellow is longer than green. Orange is longer than yellow. And red is the longest of all the colors. Notice that infrared falls after the red. Infrared means almost red. And on the other side of violet is ultraviolet, meaning very violet. Once we have separated out a star's spectrum, we can determine not only the elements it's made of, but also information about the temperature, mass, density, and magnetic field of the star. And though all the images that we take with the Webb, the Hubble, and other telescopes are both beautiful and informative, there is a challenge we have with these images. Take a look at the colors in this image. Looks like green sky, orangey clouds, and pinkish stars. But are these colors real? Is this how it would look if we could fly into space and visit this location? The short answer is usually not. We know the colors of the rainbow correspond to waves of different wavelengths. But what would colors of other wavelengths look like if we can't see them? Do X-rays have color? The answer is no, they don't. Visible light wavelengths are the only part of the electromagnetic spectrum that has color as we perceive with human eyes. Images taken with a telescope camera are taken at a specific wavelength, so they are monochrome, or without color. But since a bunch of black and white pictures are pretty boring, a color is often added to make a picture more attractive and easier to see details. Often, multiple images are added together. Here, 3 different photos were taken, and each one was assigned a different color. A picture taken in the red part of the spectrum was colored red. Another in the green part of the spectrum was colored green, and a final picture in the blue part of the spectrum was colored blue. This image of Mars is what we call a true color image, meaning that this picture of Mars looks as Mars would actually look if you went there. But that isn't the case in this image. 2 pictures were taken in the red part of the spectrum, but one was colored red and the other green. A third photo was taken in the green part of the spectrum, but colored blue. The images were then combined to make what is called a false color image. So this image is not what you would see if you could fly to this nebula and look at it directly. If you're taking images outside of the visible range of wavelengths, those images are always false color images. Many captions will tell you that they are false color, but they won't always do so. If you're looking at a picture that's in ultraviolet, X-ray, gamma rays, radio, or infrared rays, it must be false color. Our final task to finish off our Unit 1 material is to use what we know about patterns, types of light, and colors to actually do some science. We'll be looking at data the Rubin telescope people put together to learn about astrophotography and the celestial objects they image. These 2 images are 2 pictures of the same galaxy, but using instruments collecting light in different wavelengths. What are some of the differences you notice?